I'm starting the recording. Did everybody get my note on Canvas on where course materials are? So again, all the lectures will be recorded and posted within a day. Are there any questions about syllabus and sort of just how do the course rules work?
This isn't exactly about that, but do I need my laptop today?
Today? No. So we will actually first go through linear algebra review. So how many of you are parallel to this class also in math 427J or whatever its name, differential equations? Well, most of you. So basically that's where linear algebra is tackled. You might have had some in high school. Yes? No? Maybe? Or maybe you don't remember anymore? So we will actually go through a pretty fast-paced overview for the purposes of this class, because linear algebra, or rather matrices and vectors, is how we store information and refer to it. And it's underlining any kind of programming because you got to store information to be able to use it and refer to it. So from that standpoint, we will just go a rather fast-paced overview, and then you will kind of redo it again. Or possibly you're doing it right now already in differential equations, because that's where linear algebra is used. So first part of the course will sort of be on paper. And the reason why we want to, ultimately, the point of this course is not to do things on paper, but to use computers to do them for you. Okay? But we will first go through things on paper so we know how to check computer whether computer is doing the right thing. And that's an important part of doing any kind of program. Any other questions about the? All right. Well, then I will continue. Does anybody need a copy of syllabus? I have an extra few extra copies. Okay. If you do, well, they're here. If not, it's available as a PDF. One more thing is that I sent, I believe, did I possibly, if not, I will send right now. So I am right now kicked out of my office for next 2 weeks because of HVAC replay. The office is there, but it's really kind of warm. And the air is kind of stale. So I'm actually, for your information, often hiding in 3110, but you can't enter a lab with flip-flops, so that might be a prohibitive part for you. So email me before you, instead of just like stopping by, because you will not find me in my office. I will hold my office hours for those 2 weeks. I'll just find a table in student lounge, and I'll be starting Wednesday. I'll be 11 till 12, or basically before this class in student lounge and available for questions for the 2 weeks until I get back to my office, because I do like my office. So anyway, so that's sort of like just be mindful of that. And that might be the case for a number of your courses. For like half of fourth floor is kicked out of their office. So just have that in mind. It's a little frustrating, but oh well. And then announcement that Gabby wants me to make is that there is corporate office hours next week, Tuesday, Thursday, Friday. So you can kind of drop by and just talk to people who are going to be hanging out there. What's the point of that? Why would you spend 1 hour of your valuable time?
No.
Knowing people, getting to know people. You want to, and that's important. So if you're right now thinking, I don't know what to ask. I appear to be an extrovert, especially when I'm standing in front of the class. I'm kind of 50% extrovert, 50% introvert. It kind of applies to a lot of us. So often I just want to hide. I want to talk to people. I get my talking done and I'm social for 50% of the time, and the rest of it I'm like, no. So if you find me in such state, don't be surprised. So part of it is that just, even if you don't know what to ask, just show up and say hi. And don't be afraid of being a little awkward. Say hi, here's my name, or whatever. If you have a resume, drop your resume just because. If not, just say hi, okay? Likelihood is, and that's the beauty of office hours, and that applies to faculty office hours too, is that there might be somebody there too So you're not going to even have to ask a question. You can just be there and see what their questions are. And then when you see their questions, you might actually think of a question. Okay? So just show up. Show up, say hi, or whatever. And just the best thing you can ask is like, well, what do you do? Whoever that is going to be there. Okay? And that's the question you want to start asking anybody who shows up from industry. Our industry is small and it's large. It's small in the sense that soon enough you actually know that you realize that you know a lot of people, and there's not that many petroleum engineering departments. Yeah? So there's like 20 plus possibilities for people to have their degrees from, as compared to chemical engineering, where every university in the country pretty much has a chemical engineering department. So in that sense, it's small. At the same time, what industry does is large and different. So there are different flavors of it. And you want to start asking yourself, well, which part of it do I like the best? So I can align myself accordingly and look for a job accordingly. Do you seem to like breaking rocks? You should go in drilling. Are you more excited about the chemistry of fluids and how can they change phases? Well, maybe you need to go into reservoir engineering. But you need to know that about yourself. Opportunities are out there. How are you going to align with them? So basically, through interviewing people, hey, what do you do? Or maybe you're just like business side of it. Hey, okay, there's plenty of that. And there's plenty of money to be earned. So that way you will choose your classes accordingly. You will choose your organizations to hang out with accordingly, based on like what you just feel like doing. And like, you don't have to even question it too much. I like how fluids move. I don't know why. Doesn't matter. Okay? Hence, I'm doing fluid dynamics. Okay? And I happen to really like how it happens in porous materials and moving through the rocks. So, just kind of, those are the questions. Have it in the back of your mind. Store the library of people you talk to. Maybe you want to keep up with their LinkedIn accounts. Then you can later, most often than not, you will have your question later, like 3 months later, and the person you talked to 3 months ago. Right? But if you have their LinkedIn account, you can actually go and A, get in contact with them, or B, see what is their educational experience, what is their path, so you can chart your own. So in that sense, again, there's plenty of good opportunities out there. I can number them for you. I can't tell you which one you should be pursuing. Only you can that. Your mom can't tell you either. She probably wants to, but you still have to be in charge of that for you to actually be successful with it. So again, just drop by and use these are the great opportunities. This is a better opportunity than Expo. Expo is a bit of a zoo. Okay? And those of us who are 50% introverts, they're like, oh my God, so many people. Okay? So you might not function the best in the environment that has too many people around there, and you have to be on your game. Okay? This gives you a little bit more of a one-to-one that is both a little scary and more comfortable at the same time. Okay? But you have to kind of learn to swim in both types of events. So go learn swimming. Okay? Jump in and learn. Second option that I like to talk about is I'm behind an email that went around, which I don't know, where is my, I will pop it up soon. Good news about having a weird name like mine again is actually I'm kind of unique out there. Let me navigate to my personal website. So I'm advertising at the department something called Team Energy for running. So if you're interested or remotely interested in running or walking a half marathon or a full marathon, depending on where you are, it's a pretty good experience. I started running way older than you are now. I was 28. Before that, I would just do maybe maximum of a 3 mile walk or run. Right? And what's really cool about this experience is that you start training now, and little by little, by just by showing up. In everything else, I'm 4.0 GPA. In this one, I'm a C student. I just show up. Okay? Show up and somehow do it. And keep doing it. And over 6 months of that, you actually can finish a 13.1 mile distance or a 26.2 mile distance, depending what you were running for. Though the second one is a bit of a better chunk of your time, okay? Which I, for myself, decide that I don't want to invest right now. Okay? But that's, again, your personal decision. So it's a kind of a cool experience. It also provides some time off when I'm running. I'm meditating. I'm not the person who can sit and meditate for the life of me. So I gotta be in motion. That happens how I function. So it's, again, like just seeing it happen over 6 months is actually kind of a really neat experience and can show you what can happen if you just show up and keep doing something. Okay? And I think it's a good outlet from all of the academic stresses. It's a definite good alternative. So if you don't find that, find something else. I strongly suggest that you have something. But the training so we train with Austin Fit, where there is all kinds of paces. I'm in the slow one. I go 11 to 12 minutes per mile, but I get there. Okay? Fast people go 6 to 7 minutes per mile. They can do their thing. Okay? I have what's called slow twitch muscles. And I can go for long, but slowly. Okay? And there are people who walk. 13-mile walk is a decent walk. And most people drive that distance. Okay? So again, wherever you are on the spectrum, there is space for you, and there's a group for you with your own pace, and there's a volunteer coach that can help you with whatever issues show up. Even if you just kind of decide, let me try and see what you're going to probably do, even if you drop out midway. And it's okay, I'm not going to come after you and say, I don't micromanage that. But you will maybe in the process complete your first 6-mile run. What's wrong with that? Pretty cool. And this provides sort of also a social environment. I frankly don't like running more than 5 miles unless I have some company. So in that sense, it's social. So give it a thought. Ask me questions if you have any. And if not, you can just also show up. So the information is in the email or on this website. And these are basically, this is year 2013. And actually, this guy ended up 4th in the full marathon in Austin in February. And just to give you the idea, so he ran full marathon in 2 hours and 40 minutes, whereas at my fastest, it takes me 2 hours and 15 to run half of it. Just saying, there's a spectrum out there, okay? All right. So let's get back to our introduction. We left off at the motivation part, and the last part of the sort of a long time I spent on this slide was that typically we have, for the same things that we study, we have scientific disciplines and engineering disciplines. Science likes to isolate specific mechanisms as much as possible and control as much as possible to reveal what the mechanisms are. Engineers do that too, but engineers at the end of the day have to work with whatever they have to work with, okay? So they have to build the bridge in whatever environment needs a bridge. They have to go in subsurface in our case, no matter how difficult it might be or how deep might be. And I would say that, frankly, drilling some of the deepest or longest wells go about 10 kilometers this way and then 10 kilometers this way, often under sea or ocean. Okay? That blows my mind because you got to drill the rock all the way through, okay, to put the tubing in. That blows my mind more than going to the moon. Okay? Going to the moon has its own challenges, but you can kind of see the path. You just, as long as your speed is higher, you have fuel enough that will pull you out to the orbit so that you get out of the gravitational influence of this Earth. You're going, right? Whereas this drilling through the rock business is a little more uncertain. So in my personal opinion, it's much more fascinating, but that's why I'm in this department. So, that's how it works. So again, our tools for getting the knowledge are typically theoretical, experimental, just go in the lab. Also try to isolate the system and control for certain parameters and do it. But recently, and since the development of computers, computation as well. And computation, basically, this class is supposed to introduce you to the computation since it's the most recent tool. And I have like 3 little pictures to kind of depict that. So when we think of theory, we think of theory of relativity first, and Albert Einstein is the face of that. This was sort of like a setup, acoustic setup, so it happens in a lab, from one of my papers. And this is basically this is a computational world. This is a representation of a reservoir, which is divided in these individual blocks, which are individual units that we use in computation and we use to solve equations on. Okay, so if you want to, why would you kind of need to model and program is essentially, I'll let you watch this YouTube kind of on your own. But Dr. Oden is here from Oden Institute for Computational Engineering and Sciences, and basically he briefly in 2 minutes explains his route and how he became a computational engineer. What I'm going to say is that computation and and whatever you learn in this class is broadly applied. So computation in itself is not something that is specific to petroleum engineering. You're going to learn in reservoir engineering, 2 or 3, how to do basically simulation that is very specific to this department. But other than that, you do need to understand that like it broadly applies everywhere. Okay? So basically, the tools that you learn here are widely applicable and don't make you just a petroleum engineer, but essentially it charts a path as a computational engineer. And that you can apply more broadly, and you probably will. So there's nothing saying that just because you're here in petroleum and geosystems that you are specifically work in petroleum industry or environmental engineering your entire life. Life changes. Life changes on you, and you change accordingly. So basically, you can think about it as a broad, sort of a broad education that can be applicable everywhere. Now, just a bit of a history, because we're a little bit too much used to powerful computers. The phone you have is a computer, and it's more powerful than a computer that sent Apollo 13 to the moon. Okay? You use it for relatively trivial things like, connecting with your family or liking pictures of cats on Facebook. Okay? But that said, the computation and the development that goes beneath it is kind of actually mind-boggling. So let me give you an example of something that we're gonna these days just taking for granted. Nowadays, when you post a picture on Facebook, then Facebook goes and starts labeling and tagging people in that photograph for you, doesn't it? So it pulls up and it says, "Is this so-and-so?" And you're like, "Oh, wow, yeah, it is." Okay? And soon enough, you won't even think about it. You'll just post it, and it's going to be done automatically. Underneath are pretty powerful algorithms comparing photographs and specifically recognizing a person in the photograph. Mind you, we're all people, yes, but we're all kind of similar. Okay? From the photograph, sorry to pick on you, but the photograph perspective, what is the difference from our faces? We both have glasses, we have dark hair, right? Picking out the differences is non-trivial, and the algorithms that go underneath are pretty powerful. And it involves a buzzword that I'm going to mention throughout this course called machine learning. Even more so powerfully, right now, you know, if you take my photograph now, and you take my photograph 10 years ago, or even 20 years ago, I'm 42. I haven't changed that much. I happen to have the same hairstyle actually too. Last time I had short hair was 20 years ago. So essentially, yes, there is plus minus wrinkles and a little bit of weight, but you can obviously see I have formed at the age of 20 or so and stopped kind of changing considerably, right? And after that, I'm similar to myself. Okay? My Google Photos recently, I have a daughter who's 2, okay, and a son who's 4. I picked up my Google photo of 2 of them, and my Google photo suggested, hey, is this, and there's a little picture of my daughter, her name is Zara, and a little picture of Dario in that, and it suggested, hey, is this, are these 2 people in these pictures? And I'm like, yeah, they are, you spooky thing. And I click on Zara. It had figured out every picture of Zara I have in my Google Photos since she was a baby. 0 to 2 years old, you change the most in a short period of time. The freaking algorithm figured out every picture, okay, since she was a baby. You know how it got that data? That data, that requires training in machine learning, okay? So the algorithms have seen a lot of babies over their course 0 to 2. Why? Because most of the proud moms and parents and grandmothers and so forth post regular picture of their offspring on Facebook, which Facebook and Google and so forth use to train their algorithms. It took a lot of computing, a lot of training and developing a lot of algorithms behind for something that we just take for granted. It's not easy. It's a little spooky too. Somebody takes a video or a picture of you, post it somewhere, and you can be recognized. Okay? So every time Facebook announces, hey, post a photo of you 10 years ago and now, that was a fad 3 months ago. Well, good job, Facebook, collecting data. Labeled data. Okay, that is powerful in data science. Okay? So, what I want you to start thinking about in this course is, so those are somewhat, maybe you can call them trivial examples in our day-to-day life. But I want you to start thinking about what type of data do petroleum engineers work with? What type of data do we need to train similar algorithms to recognize events that are related to petroleum engineering? And that's not easy because we work with complex subsurfaces. We often like to describe it in simple terms. Oh, porosity. Everybody knows what porosity is? Permeability, right? Properties that we log in well logging, right? But I want you to start thinking about these just like those pictures. Pictures are matrices, by the way. We're going to get to matrices, but they're matrices of colors, and colors have just numbers underneath. So they're matrices of numbers. We work with different matrices in petroleum engineering, matrices of porosities and matrices of permeabilities. Okay? But can we also equally, as far as computer is concerned, matrix is a matrix. Okay? As far as math is concerned, matrix of porosities or this picture, two similar, very similar objects. Okay? So I want you to start thinking in more general terms when you see these things that happen in your day-to-day life, and try to connect them to your experience as a petroleum engineer and recognize the similarities in type of data and type of algorithms or approaches that they, okay? Because I'd like to, in future, be able to throw in information about my new well log, okay, or set of well logs rather, about the reservoir into Google Photos or whatever database, okay? And the database should suggest, by the way, this reservoir is similar to reservoir A, B, and C in this basin, or in this, yeah. Can we do that comparison? Just like recognizes similar faces in photographs. So what are the features that you need to recognize in those well logs that would be similar to something else? That's a similar type of questions. And some similarities like this that I'd like you to do. Now, I will actually ask you to do this over the weekend, to watch these two videos, and then we will actually just post a simple question on some of the parts of this video, on basically history of computers, just for you to understand that these powerful computers that we wear today, could be your phone or even watch. That's just too small of a screen for me, so I'm still analog in my watches. Okay. But that's it. You know, computers have gotten smaller and everywhere. I can, if I wanted to, log into the heating and cooling system in my house and basically set it to a certain temperature. Okay. So that requires a small computer right there as well. These days, computers show up on fridges, on cooking devices, you name it, that you can kind of talk to wirelessly. And so again, we today live in the age of computing, but that hasn't been a long of an age. So the way a computer, compare your phone to this, looked like in 1946 was the room. Here's two people for scale. Okay, so it took a moment in technology to actually devise it to be much smaller. And just a couple of facts is in 1963 there were 15 computers in the entire state of California. In 1973 there was one computer on this campus, and whoever wanted to compute something had to go to that computer. And there's one recent movie that I adore that actually shows hidden figures. It shows a lot of things and goes over a broad range of issues. But one of them was like they were installing computer at the time, and it was this huge thing that filled up a room, and they had to adjust the doors for it to be able to be moved in. It took 3 months to install. Then once it was installed, they didn't know what to do with it. Okay? And it's actually a group of women, human computers. They were called human computers at the time. Figured out, so the lead of the group basically figured out, I think I have another slide, so if you watch that movie, please watch it. The lead of the group basically, here's her actual picture, figured out how to do it. Okay? In the face of all other issues of not having enough, or almost any women in computing at all, not having enough of African Americans in computing at all, and so against all of those adversity, they figured out how to do it. Okay? But again, human computer, or people doing calculations by hand, was a job. Okay? Today, we give those jobs to computers. Okay? But we need to know how to program them, okay? And how to talk to computers, and this is what this class will start from. So again, please watch the movie is excellent. And one also other thing that it shows, and it shows again the leadership on the part of the lead of the group. She recognized computers are coming, and that's a new technology that we have to adapt to. And if we don't adapt to and learn how to code and talk to the computers, we will lose the jobs. So what she, as a technical lead, did, she taught herself how to program, and then taught her entire group of 20 of how to program. And by the time they figured out how to install the computer, okay, she just showed up and said, hey, and I have 20 people who know how to do that. That's what leaders do. And you will, in the same industry, more than any other, be often faced at the crossroads. That's a crossroad, okay, of a new technology simply coming and overtaking. And you can go against it. Good luck with that, okay? And dig your feet in and say, I'm not moving, I'm staying whoever I am. Okay? But likelihood is you gotta change. So you've gotta change, but adapt quickly. And it's the leaders that actually see that and kind of lead an entire group in that direction. So So that's something to think about, because I don't know what technical change will be there 10 years from now. Okay? Something that we haven't really dealt with. Everybody has heard of shale. Okay? In this industry, we didn't do shale 20 years ago. Okay? That kind of showed up when I came here as a young professor at this department. I'm like, okay, I got to now do research in shale. That means research on length scales that are 1,000 times smaller than what I was used to or trained to do. Right? Gotta adapt. So we all do that, and you will, in your life, or your working life, for 30 to 40 years, you will go through 2 to 3 of such shifts. Okay? So that's something that you have to, and whatever your undergraduate degree teaches you, we should teach you how to learn, because you will keep learning. So all of these classes and the system we go through in classes to learn basically just teaches you how to learn, how to pick up a book and acquire new knowledge. And give yourself, typically, 1 semester is actually a good unit of time to learn something new. You're not going to learn it overnight. You have to ease ourselves into it. You're not going to just sit in 1 week and learn everything, because that's not how classes are structured here, are they? You're not taking 2 weeks of one class and 2 weeks another class. We don't have modules like that. That's why. Because humans learn better at this, like, let's introduce new stuff 3 times a week. Not 6 hours today and then 6 hours tomorrow. So we take a little time to actually acquire and use to learn new knowledge, and basically you will learn how to learn and move on from there. Anyway, so computational engineer to this date, and computers are not going away, is a powerful career path, and it doesn't really matter which type of engineering you're in. Yeah. Now, this is the movie I will play, at least one today. And this is just to also, you will be ready to punch your computer at least 10 times during this semester, and probably more, okay? When the communication between computer and you gets a little more frustrating. But I'd like you to understand that today, things are still way easier than they used to be. So I'm not old enough to have worked with punch cards, which is how data used to be stored, okay? But Dr. Ballmer is. So we interviewed Dr. Ballmer, or rather 2 students from this class interviewed Dr. Ballmer in 2015. And I'm gonna let you, over 5 minutes, learn how computing
When did you use punch cards, and what was it with industry? Was it with like schooling, and then what did you use them for?
When I learned how to program at the University of Texas from about 1973 to 1979, punch cards were how you did it. Punch cards were the way you communicated your program to the computer. And they had some typewriters, basically, and you would put your cards in and they would be sucked into the typewriter. And then whatever line of code, 1 line only, 1 line of code you typed in, and then it would punch a hole at strategic places across the card. So if I had a program that was going to have 10 lines of code, I would have the first card would be, they called that the job card. That's how the computer knew new job. Mm-hmm. Then after that came the cards that were line by line by line by line of the program. Then there would be an end card, and then if you had any data, that came next in the format that the program told the computer to expect the data. And then last but not least, as I recall, there was a green card that was the end, termination of job. So everything between the start card, the job card, and the termination green card, that was your program and your input data.
Oh, wow.
So if you weren't good at typing, this would take a long time. And so let's say I've got my little program deck, and I take it over to the computation center at the University of Texas, and they had some card readers. So they had big trays, and your program would go at the end of the tray, and they would take that one, put it in, get it, read every card, put that deck back in the output, and then you would wait. So the computer now is thinking about getting to my program, and it finally spits out a hard copy, and it would show the listing of the program. It would show results if it got to the results. If it thought there was a programming error, it would put a code down at the bottom. You need to look at this line. There's something here I don't understand. So then you'd have to go figure out what was wrong, retype the card, resubmit the job, all over.
How long would if you just wanted to do one normal job, how long do you think that would have taken?
Well, it depends on how many people are using the computer at that moment, because in those days, the University of Texas had one central computer. Every place on campus fed their programs to that machine. To make a long story short, if your program was really a small program, well, you could probably get that back in an hour. But if it was a big one, or if there were a lot of people using the machine, if you got 2 runs per day, you were probably pretty happy.
Wow. Do you ever miss punch cards?
No.
Were they phased out because of the computers and like the processing power of all of that?
No doubt. No doubt. The processing power and the storage capacity of computers started getting to the point where I could take my program and I could sit here at my terminal and I could type in my program electronically and I could save it as an electronic file. And then whenever I was ready to submit it to the computer, I could. So as the data storage capabilities got better and better and better, nobody really wanted to do punch cards. It was the only way you could get your program recognized by the computer. But in 1973, trust me, that was whiz-bang stuff. That was the cutting edge. That was the way everybody did it.
Again, when you're ready to punch your computer, just remember you could be doing it with punch cards. So let me imagine a scenario of you doing your final, or either homework or maybe final project for this class, and you're punching it on cards, and you're carrying your tray of cards in the bus, and there's one of these Texas downpours in December, right? And they're all wet. Goodbye. You gotta retype the stuff. These days, whatever you typed in, you did type it on a computer, and there's likely a file. And if you were using the latest technology, your file is on a cloud. So it could rain on your computer, but you still have access to that file from whatever other computer. So back to my point, time to, if you haven't so far, organize your files on cloud. Name of a cloud doesn't matter. UT has UT box that all of you have certain storage on. So I would suggest that you have that box and you have it synced to your computer. I'm going to show you how it looks in my case. So the UT box is synced as a folder on my computer. The moment I'm online and type in any changes, say I type a change to this file, it's going to actually go and get updated to the cloud. So I actually have a folder. This is my folder, box folder, that is always synced to this computer. Something happens to this computer, I can log into another computer and download the box sync, and it will organize the same folder with the latest files that were saved last time my computer was online. Okay. This is not all of it. I actually have close to 2 terabytes of data. Most of it sits in the cloud. Okay. I've been collecting data for a little longer than you. I'm going to quantify how longer. Okay. So, and the data that I work with in research is kind of bulky. Okay. So not all of it is on my computer. And I can also turn things on and off. So I was recently traveling. The travel suggestion was not to carry any sensitive files, certainly not any UT files to that country. So I basically just turned them off from my computer. And I traveled what I need to travel with. So there's certain flexibility, and you should set that up now. Because I guarantee you, if your computer is going to break down this semester, it's going to break down in the middle of some important project that you need to submit. That's just how it works. Okay? These things tend to happen. If you're going to spill a coffee on top of it, you're going to spill a coffee on top of it when you're most tired and you have 3 exams going. There's just more likelihood that it's going to happen when you're stressed out. Okay? So, being an engineer, guard yourself against the errors and automate certain procedures now to prevent that from happening. That's half of engineering right there. Okay? So learn certain procedures that will make you more effective at the times of stress, because when you know you have data showing that at times of stress, more things are going to fail. Okay? So I would say, at least for this class, but most likely for most classes, just organize it into folders and clouds, so when these things happen, and they will at some point happen, when they happen, it's going to look like you're the unluckiest person and it happens only to you, but trust me, that's not the case. Similar to a lot of other humans. Okay? So just prevent that from happening by organizing things. And again, there are things that are available to you free of charge. You can use any other cloud that is available to you. UTBox is one of them. Okay. Back to my... So let me just provide you with a couple of numerical method examples, just so that you get the idea of what is numerical simulation about. So numerical method is really just a series, it's an algorithm, it's a series of steps you go through consistently, and often in a very repeated fashion. So again, what computers are going through is repeating something 1,000 times that a human would have a hard time with. And basically then getting a result that is close to, not the same as the solution you're seeking for. Okay? Now, here is an example that everybody knows. And for this one, we actually have a formula, so we don't necessarily need supercomputer power or any sorts. Say you want to find the roots of this equation. X squared minus 4x plus 3. It's a quadratic equation. You probably learned how roots look like sometime in high school, if not before. So basically we have a formula and we can use a plain calculator. I don't need to do any serious programming, okay, to find the result. So basically there's a formula based on this ax squared plus bx plus c is equal to 0. Then if I plug in a and c's into this formula, I'm going to get the result that one root is 1 and the other one is 3. That's quadratic equation. Greek mathematicians way back when knew about it. Okay? Well, not all equations we want to solve are quadratic. So let's say that there's a simple or a version of an equation that we use a lot is that for pressure, volume, and temperature of an ideal gas. What is an ideal gas? No real gas is ideal gas. Some of them are close to in their behavior. It's typically gas that I could conceptualize as its molecules as a bunch of bouncing balls. I like thinking about them as tennis balls, that when they collide, they just bounce off each other and go their merry ways without any strong intermolecular forces or anything weird happening. Yeah. So really the kinetic theory deals with that. You can actually then describe this gas, these bouncing balls, and you lose no energy in that collision. You just kind of have a super elastic collision, which again, no collision is super elastic, but some of them are close. And basically that gives you this relationship, which is a linear relationship, right? There's R in there, which is the constant, gas constant that we know. So if I give you 2 of these properties, the third one is really easy to calculate. You plug in 2, you have R, and you find the third one. Easy equation to solve. Calculator will do, or even by hand. Now, most of the real gases, and I mentioned already that petroleum engineering goes to extreme depths with the temperature and pressure are extreme. Okay? Even what was ideal gas on the surface is not going to be ideal in those conditions. Okay? So we have to have a little more complicated equation. This equation is nonlinear. It sort of divides by a quadratic equation down here. and it has this both inverse linear and inverse quadratic terms, so heavily non-linear terms. How do I solve for it? Okay. I do have A and B. Those have been tabulated over time by chemists and chemical engineers. So I have those. I can find them for methane, say. So if I have pressure of 50 bar and temperature of 473 Kelvin, how do I find VI, the molar volume? A little harder, right? So this is a type of nonlinear equation where I have to find the method. I don't have a formula for it. Trust me, there's no formula for it. Okay? This is where I have to solve for it numerically. Now, what would be the algorithm? What would be your first guess? If you were required to guess, what would you do? What would you start with? Like just the ballpark of a number. You can use that ideal gas one for the first guess. So this is actually the first rule of these numerical algorithms. Even if you have an algorithm that tells you what should be the procedure for you finding this root, you need an initial guess. You need a start guess. It doesn't have to be the one provided by ideal gas law, but that's actually a pretty good, at least it's in the right ballpark of numbers somewhere. Okay? And that's what you start with. Okay? So one thing that you do without computers is what we actually do is we actually organize this equation so that it's some expression equals to 0. And now I have generalized it. Okay, so the algorithm that I can come up with is more generalized. And then I plug in the numbers, and I'm looking for what is this expression equal to 0. So I plug in my first guess, and I see how close to 0 am I. And after that, I adjust. Now, key thing is to finding a good, nice rule that I can easily tell computer to repeat of how to adjust. And then go and repeat it 1,000 times. And computer will be really fast at doing that 1,000 times. If you're doing by pencil, you're going to do that on a piece of paper 6 times and stuff. Okay? And that's actually the key of numerical computing. I have a rule or an algorithm that is easily repeatable, and I can translate to a computer to repeat. Okay? And a computer will do so quickly, way more many times than a human can. Numerical solution. I have to spend some time making sure that the results I'm getting are close to reality. That's the validation of it. And we will go through those steps in this class. I see you on Wednesday. Enjoy a long weekend. You're welcome. See you on Wednesday.